Hi. So my name is Ian Purcell, and I work with Research Computing Services at the University of Calgary. I'm going to be giving a talk on using geospatial analysis tools on HPC systems. So there's a fair amount of content I put in here, sort of more than we can get through today. Some of it goes into details that I'm not going to have time to cover, but I'm going to make the presentation available. If there's a central repository, I'm going to load it there, and I'll share my email address with you at the later in the presentation, and you can contact me to get it directly or ask any questions you want about this. So where we're going with this is we're going to look into how to do geospatial analysis without using a geospatial database like PostGIS. The way we're going to do this is through a collection of C and Python libraries that were built for this purpose. So we're going to examine which ones are required and how they connect together. And most of the time is going to be spent on GeoPandas as a pleasant interface to work with for doing this kind of work. And towards the end, we'll get into some details of spatial indexing and parallelizing these calculations. The parallelization is a little bit sketchy because a very robust parallelization becomes very complicated. So the version we're going to cover is going to be relatively simplistic, but it shows the idea. So the sections, we'll start with a quick Pandas review, and then the GeoPandas basics, combining it with NumPy, doing archery indexing, and then parallelization. So I have a couple references in here if you later want to try some of this out for where I'm getting the data from. The data is based off of the public use microdata sample from the US Census. So it covers housing data, and you can download it yourself to work with. It's an interesting data set in part because the data, in order to de-identify it, has been broken down with replication weights so that it hides the identities of people. And so computing averages is non-trivial in this data. So you can't just call an average function. So it gives us an opportunity to see some of the use of combining multiple libraries together and why this is an important aspect of doing these kind of calculations. So where we're going is if we were to import this data set, sort of the kind of calculation we're going to build towards as we go through this, where we're going to take read-in data, do a calculation based off of data that's linked to spatial, a spatial reference point, and then plot that and examine different kinds of filtering and analysis of that data. So to start with, what underlies all of this is a fairly mature topic in computer science, which involves different aspects of computations that are used with geospatial data. One of them is the analysis of shapes that are projected onto the Earth, linking data to that, and spatial indexing. So those three things together form the core of a lot of geospatial computations. There are more topics that are relevant to this, but they're beyond the scope of this talk. Some of those tools are covered by Python, which is a library I like using, but we're going to focus on GeoPandas for the purpose of this. The underlying C libraries that make this possible, that implement the standards and core data sets that have become part of the widely accepted tools of geospatial analysis, are part of the OSGeo libraries. So the three that are relevant here are Proj, GEOS, and GDAL. Proj provides projection, so it allows you to map things from generic latitude, longitude into something that we can think of as having a notion of distances. GEOS provides computational geometry tools, and those allow you to do all the calculations of whether different shapes overlap and this kind of thing, and we'll see why that's important as we get deeper into this. And GDAL allows you to link relational data together with spatial structures. And this is really the part that we care about that builds on the other two. So these are, at their core, C++ libraries, but there are Python modules built off of them that are a little bit easier to use and require less expertise in the technical details. So the first one is Proj has PyProj built on top of it. GEOS is can be accessed through Shapely, and GDAL can be accessed through Fiona. And all three of these come together in GeoPandas that allows you to do most of what you want to. One more bit of advanced information that you might want before you get into the get deeper into this is what's different about working with HPC on a cluster. So on a cluster, you have a large number of compute nodes available to you that can be accessed in parallel, and data that's stored centrally and is available to all the compute nodes. So this changes a couple things of what you might be used to from working on your workstation with geospatial tools. One thing that's less obvious, a lot of databases, geospatial databases, rely on having a server component that can't run on these systems. Any complex C dependencies like GDAL need to be built manually. And these might have been done by an administrator for your system and put into an environment module, which is done on ARC at UCalgary. And the computational resources can be allocated from many computers across the system to do a calculation in parallel that uses far more resources than any one of them could do. But that means managing memory and copies of data and all of this, which becomes kind of a challenge. For all of this, it's easier to do if you use open source tools that don't require server processes, and that's why we're focusing on the technologies that we are. Python on a cluster has some limitations that may not be obvious from working with it on your personal computer. It doesn't scale as readily because it has something called a global interpreter lock. However, if you have a C library underneath that can take advantage of some of that, and there are a number of ways of doing this, then you can actually still exploit that the efficiency of working on a system with more resources. You just have to know how Python is managing things. And so we're going to talk about that in the context of Dask, which will allocate subsets of our data to different computers. So the quick review of Pandas. So Pandas provides a SQL-like interface that allows you to analyze tables and do joins and all this kind of stuff. You also have the option to blend in NumPy for doing linear algebra and statistics. So it's a pretty useful way of thinking about data analysis, and it's sort of become the background for a lot of tools that have been built in Python for doing data analysis. So the quick version of this, I'm going to try to keep this down to a few minutes. You can read in a CSV and specify what columns that you want, set an index column for quickly sorting the data and joining. And you can see how in 2 lines you can load a data set pretty complex that has a pretty complex structure to it. It has resources for querying, so you can run query and pass it a where clause that you might be familiar with from working with SQL, that kind of thing. And it will filter out a subset of the data. There are some specifics to when query versus other methods of filtering are preferred that you can look into by reading some of the Pandas documentation on this. That's not something you're familiar with. It has a function called merge that allows you to join 2 tables together. And joining here can mean inner joins, outer joins, all sorts of things. And it gives you a lot of flexibility, and there's a lot to go into with this, but basically it allows us to compare on a row-by-row basis some match condition and mix 2 tables together on that match conditions to append data or filter. So this is going to become relevant because we're going to be combining data sets at a later point, and we'll also be generalizing this to spatial joins. There's map functionality for transforming a single column of data, and this uses a functional form. So .map takes a function and then applies that to the data in that column, row by row. There's a more general transformation structure called split apply combine. It uses group by and apply. It can combine within a single row. So here we're combining the number of persons in a housing unit with the weight for that housing unit to get part of an averaging process, and then calculating the average and the full average using a sum and then division. So here we're combining data from multiple columns, but just within one row within the apply. But it can be extended to a more arbitrary structure. So we can do applies that do both combining columns and combining rows. And so here we do a weighted average all in a single query. Okay, so that's all the pandas that we're going to need for this. It's a fair amount of content, but if you need to go back and look at that later, there's a lot of resources on pandas. All right, so what we're here for. What is essential to a geodatabase? When we use something like ArcGIS or PostGIS, what do we need from it? So we have to be able to represent spatial features, and that means having the datum and projection information, spatial indexing, that kind of thing. And we have to have a way of creating polygons or lines, things that represent subsets of space. We need to be able to link attributes to it, so we need to be able to assign data to those spatial features. We need a way of transforming that data and a way of combining different spatial features based on some set condition. So that's a lot of stuff, and Pandas clearly doesn't offer all of that. Pandas can combine spatial features, but even if we added a column representing the attributes and one for the spatial objects, we would have problems with mixing them because the projection data needs to be consistent, and there has to be an overarching spatial index to make joins efficient. So Pandas doesn't offer everything we need. However, GeoPandas does. It makes use of all those other resources that we talked about in order to implement, in addition to the Pandas data structures for handling tables and numerical operations, also the geospatial component. So it provides easy handling of projections. You can convert between different projections of the data. You can create spatial indexes. It makes life a lot easier overall. Also, the plotting maps turns out much more nicely. So a geodata is only distinct from a Pandas data frame in that it has a geoseries. That geoseries has a single projection data piece of information that's stored in the CRS attribute, and it also has a spatial index stored in the S-index attribute. Those two things make it different. The geometry column is coded as shapely objects. So Shapely was the library we talked about earlier that's based off of GEOS. And those Shapely objects have all the tools we need to do computational geometry and determine if we have spatial matches between a line and a polygon or a point in a polygon, that kind of thing. All right, so loading data to a geodata frame. If you were to try and assemble this data structure on your own, would be a lot of work. You'd have to build all of the rows, all the data into a Pandas data frame, build a column with Shapely objects, and then build these additional indexing structures on top of it. The geodata frame does this for you all in one command. You can root a file in and have your geodata frame. The geodata frame, when you just examine it at the top level with head, you can see all the data that comes with that. So it comes with information, in this case, about the area of different regions and the indexes and the name of the county and this kind of thing. And it has a geometry column. That geometry column is the Shapely objects we were talking about. So this brings us to how the underlying libraries function in GeoPandas. We can extract out the CRS feature from the geodata frame, and we'll get a WKT string. That's the string that describes all the projection parameters in plain text. And we can compare that to the WKT string that we would get in the .proj file to make sure that our geodata frame loaded it correctly, and in fact it did. So proj is doing all the work behind the scenes here, but PyProj through GeoPandas is the part you actually have to interact with. So it saves you some fussing over C++ function calls. You can just use the Python interface. And the nice thing about it is it provides us an easy way to project between different projections. So if we want to change to EPSG 26971, we can easily do that because our original data frame, our original projection was unprojected. It was longitude and latitude, which would have given a wildly distorted shape. And now when we project down to something customized to Western Illinois, we will see, or Eastern Illinois, we'll see a clean projection of Illinois that looks like the state is roughly supposed to look like. So shapely polygons. This is what does all the work. And this is the part that is implemented by GEOS. So GEOS is backing all of the work done by Shapely. And we can do all sorts of fancy things with it, finding common boundaries, finding regions of overlap, anything you can conceive of with set theory or with how you're used to thinking of geospatial transformations. GEOS is built to do that, and Shapely makes that possible from Python. So I've included here a couple problems and solutions that I'm not going to go through in detail, but if you download the presentation and you are wanting to work through this data and see how some of it works yourself, you can examine, for instance, how identifying neighboring regions and figuring out where the worst accuracy on the projection is, that kind of thing. All right. So the second topic we're going to cover in this interface, how geodata frames are useful, is how we build on this. So far we've just imported some data and projected it properly and visualized it, which is nice enough. But let's say we wanted to compute for instance, an average for every Puma district. So these are the areas associated with this microdata sample. We want to compute a weighted average of the number of people living in each household. Right? So the way we do this, we demonstrated something very similar earlier in our discussion of working with pandas. We can compute this weighted average. Where will the presentation be available? There should be a public location associated with WestGrid training, but if you just email me, and here, I can post my email a little bit later in the presentation. See if I can do that now. It's ian.purcell@ucalgary.ca, but I'll post it in a little bit, and then I can email it to you if necessary. Okay, so extending it, if we computed this weighted average of the number of persons per household and did that by Puma district, right? So this would generate data associated to each Puma that we could then plot. So if we were to join this using the Pandas merge, we would end up with a Pandas data frame, and then we would lose all the geospatial structure. We actually have to use the geodataFrames merge function, which is identical in appearance. I just emphasize this because it's a little bit different in how you call it. When you call the geodataFrame merge, you use one geodataFrame and then call .merge on that, rather than calling merge on two geodataFrames. The reason is that the merge, like a geodataFrame, can only have one geoseries associated with it. It's basically saying you can only have a single layer of spatial data that you're associating these attributes to in the end. And what that amounts to is whatever is doing the calling, then you can, whether you do a left join or a right join, determines which geoseries you're ultimately going to keep. So here we're actually merging with a regular non-geodata frame, but we're calling the merge from a geodata frame. There's only one geoseries to keep, so it just keeps that one. And we still have GeoPandas geodata frame intact, so you guys still have all our spatial structure. Once we have this with our combined data, we can do queries on this spatially linked data. We can do a query the same way we normally would, just filtering out only those things with a relatively high average number of persons per household. And so when we plot and we query, we can see just that average, just the districts that have that high average number of persons. And if we want to zoom in more carefully, we notice in this that in the northeast region of Illinois is where all the high number of persons are. We can use spatial index-based filtering. So what this amounts to is picking out spatial subsets. All the stuff we did earlier with querying with average NP, that's just an attribute. We're just filtering out rows of the table based on that attribute, just like we would with the Pandas data frame. There's nothing particularly spatial about this, other than when we plot it in the end, we see something spatial. We can introduce into that this .cx operator to also filter out a spatial subset. And that allows us to zoom in on particular spatial regions and look at those in terms of their like a little bit finer of a resolved chloropleth plot. And we can combine that with querying. So now we're only seeing in that northeast quadrant the really high end of this spectrum of values, and it's filtering out the districts that are of interest. So all that together, what we've introduced is spatial indexing for filtering, computing values that can be plotted spatially, and making use of the plot functionality to actually see the maps that are being produced by these filtered data sets. To go further and see something more interesting, we want to link different spatial data sets. And this gets into spatial joins. Spatial joins are a fairly interesting topic in that there's a lot to know about different kinds of indexing options. But we're going to focus on just the two most straightforward ways of doing this that are available in GeoPandas. The way to think of it is that if you're joining two tables in a relational database, you're going to compare every row of the two tables, and you're going to see if they match on some criterion. And if they match, you keep the pair joined together. We do the same sort of thing in a spatial join. We compare row by row, but the match criterion isn't text matching. It's not saying that index 1 equals index 2, or like number of persons 1 is greater than number of persons 2. We're not doing that kind of comparison. We're comparing two spatial objects. And the ways we're going to compare them are all set theoretic. So contains, within, like things you can define in terms of intersections and unions and that kind of thing. So the one we'll have in mind for this as a sort of a straightforward one is an intersection. So just we want to keep any pair of features that intersect from the two tables. So we read in our file and we look at the two different spatial structures. The file we read in was for census tracts. Those tracts have a much finer resolution. That's what you're seeing in the top image there. They're much smaller. The tracts are much smaller than the Puma regions. So if we want to attach to each Puma region every tract that intersects it and the data associated to that, and then average it in some way or take a maximum, that is going to be something we have to do with a spatial join. All right, so let's add some data to the tract level geography. So we generate some normally distributed random numbers and tack that on as an additional column in our tract data frame, geodata frame. And this is sort of what I was talking about earlier. GEOS is going to do the work for us. So GEOS is the computational geometry part of the underlying libraries. And what GEOS is going to be doing is it's going to be taking these regions that we're comparing and seeing if they match on some geometric criteria. So it will calculate the intersections. If that is not fast enough, and in some cases it won't be, when you have very large tables of polygons, you'll need to take advantage of some spatial indexing. To go beyond GEOS, R trees are a good way, and that is actually added by additional packages. So R trees will, as they're implemented for GeoPandas, will use bounding rectangles for the polygons and then try and match those first so that the number of comparisons GEOS has to do is smaller. And the library that adds that is called rtree, and it's really just a wrapper for libspatial index, which is a C library that does a lot of extra work that allows you to minimize the number of GEOS computations you have to do. So if we get that built and installed, we can continue and we can use sjoin and have it work with an R tree first before it actually calls geos. And that will accelerate the calculation enormously because a very small number of geometries will be compared. In contrast to if you do the full join without an R tree, you have no index to work from that will select off subsets. So the R tree can be kind of thought of as analogous to a binary search tree. The way that form is used for indexes in relational databases. It makes the number of comparisons you have to do the logarithm of the original number. It reduces the amount by a tremendous amount. It reduces the number of comparisons by a tremendous amount. So R tree will, especially when you have one geometry that's much finer than the other, it will make this enormously faster. The syntax for it is pretty straightforward. Sjoin is basically call GPD sjoin and then pass the two data frames. And the same way as with merge, you have a how and an op. So how is actually, in this case, going to be left or right, and will specify which of the geo series gets kept. When you say specify an op, that's going to be the rule that's used for the comparison. So there'll be things like intersects, contains, within. So we can left join the tracked data to you can left join the tracked and PUMS data. So keeping the tracked level, but appending the PUMS data, all the PUMS regions that intersect it, all of that will be collected together into one based on the intersection rule. So once we get that, that'll all be stored to this new GeoDataFrame joined data that we can then analyze. So joined data, we can look at what it is, and if we examine joined data, there are multiple matches that we get. So every tract or every PUMS will intersect multiple tracts for the most part, and some tracts will intersect multiple PUMS. And so we'll get more records than we had tracts. But when you filter it out, you can see that there's agreement, like all the tracts are represented ultimately. So that's the side that's been kept. And you can do grouping calculations based off of this. So for instance, we can define something where we calculate the max over all of the average NPs that we wanted to append, and append that at the tract level. So now to each tract is associated something that we calculated from the PUMS data. And the result is a plot that has multiple tracts that have the same average NP selected because they all intersected with the same PUMS region. And that was what got kept. So we can filter that further, and we can also view the other data that's associated, the tract score data. So the data, both the grouped data and the original data that we generated on the tract level, all that's available to us now in this new data frame that stores the tract level geometry, but has all this other data associated with it. And we can filter it the same way we did before to produce subsets. We can combine criteria from the different data sets we've joined, producing like a more complex join criterion. So that is everything I wanted to cover in how to use GeoPandas. I went through it pretty quickly because I wanted to get to this section. And the parallelization stuff gets kind of fussy. So I'll spend a while on this. There are two main pieces of writing that I'd recommend taking a look at if you want to dig more into parallelization with GeoPandas. The main example I'm going to talk about is based off of an article written by Ravi Shekhar. And it is a relatively straightforward implementation of GeoPandas using Dask. And it doesn't really manage memory very efficiently. And for deeper analyses of how to make memory handling more efficient, there's work done by the creators of GeoPandas and Dask working together on a pretty neat project that, as far as I know, is still in development. But there's a lot to read on that, and I'm going to talk about some of those later ideas, but mostly focus on the simpler example of how you can distribute a calculation by subsets of rows. So the main things to be thinking about with parallelization for this is that every test for intersection can be thought of as independent, right? Every pair of records you compare is a separate intersection. And whether they intersect or not is a calculation that can be done without knowing anything about the outcome of any other calculation. This is a good kind of case for sort of embarrassingly parallel calculations. We know that each of those comparisons can be done by a separate worker. We don't want to necessarily do it that way. We probably want to batch them together so it's efficient. But that's the main idea that's going to be at work here. We're going to talk about multiprocessing versus multi-threading, GDAL and archery. A little bit about archery serving and data frame subclassing. So, what is Dask? I'm going to be using Dask in these examples, and the reason is that it provides a sort of relatively friendly interface for doing parallelization. If you want it to be efficient, you have to get into the gritty details. But some ideas are easy to represent in Dask and while still presenting code. So that's why we're going to be using it. So Dask can be thought of as sort of a preprocessor. It's something that if I write some Python code, I can give it to Dask and it'll turn it into a graph of operations that can be done efficiently in parallel. So it'll do some transformations on it to make it simpler and make it easier to split between multiple separate workers. So when Dask is done doing that preprocessing, without doing any calculations at that point on the data itself, it will submit the work that needs to be done to a scheduler that you specify. So a completely different library and set of tools will be handling the rest of it from there on out. Dask isn't doing that work, it's just feeding the restructured problem to something else. So this kind of minimizes how much you have to know about parallel computing in some ways, but really if you have to debug it, you have to be able to understand what Dask is doing and why. So Dask has some optimized simplification processes that are specially tailored to some common libraries. So it has some built for NumPy and some built for Pandas that it implements as easier to use tools than its main body of tools. And so we're going to focus on one of those. Because this is so close to a Pandas data frame, we're going to be making use of the Pandas interface, the Dask DataFrame, which is very similar to Pandas data frames, but it supports splitting things up, and we'll get into that in a bit. So a Dask scheduler is what calculates the task graph and gives you an actual result at the end. So what gets used depends on what part of Dask you're using. There are two pretty different parts of Dask, and the same task graphs will work with both of them, but they function very differently. One of them is a local cluster, and that just works on one node. So on an HPC system, if you submit a request for just a single node with a bunch of cores, you can use a local calculation to do that. And that can be done with threading or with multiprocessing. And choosing between those is a somewhat involved decision, but simpler in this case because threading doesn't really work with the underlying C libraries. If you're using multiple nodes, you have to use Dask.distributed, which basically means using MPI for pi, is the real library that's doing the work of getting the calculations done. There's a large array of options provided by Dask.distributed. Most of them are not very helpful on the kind of shared clusters that most of us work on. MPI is basically the way you'd be doing it. You'd submit a request for your full resources, start up your scheduler, and use MPI effectively to make use of multiple nodes through Dask. We're going to focus on the single node case because it's a lot easier to think about. So Dask DataFrames and partitions. What Dask DataFrames do differently from Pandas DataFrames is they will take the many rows in a data frame and split them into chunks, partitions of smaller subsets that will be done as separate tasks. And this is where what I mentioned earlier comes in. Each intersect comparison is independent of the others. So in that sense, those can all be thought of as separate tasks. And it's easy to allocate those in parallel without any special communication going on. This is exactly the case where Dask DataFrame is a good data structure to be using. There is a hiccup here that we'll have some lines in this addressing. For a spatial join, you're dealing with comparisons that rely on that geoseries. The Dask DataFrame does not preserve that geoseries information. So we're going to have to break it down and reconstruct it in each one. There are better ways of doing that, and we'll talk about that a little bit. But essentially, we're going to turn our data frame into a Pandas data frame, and then farm that out to separate workers, and each worker will do a subset of the spatial join comparisons. Here I'm really talking about the parallelization of spatial joins when I talk about using Dask data frames. If you're doing really involved raster calculations, you're actually doing something a lot more like a NumPy ND array, and there are better ways of doing that because a lot of those can be done with block parallelization rather than by rows. So that's a thing to think about when you're doing that, but beyond the scope of what I'm going to talk about in this. We're just going to focus on spatial joins. All right. There is a function for the Dask data frame called map partitions. That is an interesting question. So will Dask eventually support geodataFrames? My understanding is yes. They talk about it explicitly in the their example on subclassing Dask DataFrame, and there's a project that, last I checked, is under development still that Matthew Rocklin is working on. There are some technical challenges involved, and they're trying to implement a different way of referencing GEOs through Python. And this is something that's still being developed. They haven't released it officially as part of Dask, but it will be very cool if they do, because that will save anyone who wants to do this a lot of work. But in the meantime, they do have a lot. Matthew Rockman and Chris Vandenbosch has a lot they've written on this process and how you can implement part of it. They have a GitHub repo that's linked in that the article that I included a link to in that in the earlier page. But so there is work that you can see on it that would be a starting point for doing your own calculations with that, but it's not released officially as part of Dask. But you know, it may work. I don't know how far they've gotten in testing, so I don't have an answer in the long run, but it seems like a lot's been done on it. Okay, so so map partitions, the way that it's going to work is that you have to think of it as something that will do the same thing, sort of, to every partition. You're going to pass it a function that you want done to each partition, and it will transform that partition, like each partition separately on a separate worker. You can kind of think of this like the group by apply framework, except now you're allocating each of those tasks out onto a different worker using different computational resources. So you've sort of sidestepped the entire global interpreter lock, and you're doing a full calculation, one that may not even be very friendly to parallelization in and of itself, on a separate worker, just based off the fact that you can treat the row chunks separately. To implement this comparison, what we're going to do is we'll define a function that will do a join for us. So we will do multiple subjoins and then combine them all back together. And this will allow us to handle a lot of data at once. We'll run into some interesting challenges when we try and do this, because there are a lot of things with data sharing that get complicated when you have multiple separate workers. So I'll demonstrate some of that. So yeah, the custom join function itself would be something that takes a data frame as a function and then transforms it and returns a result that can be digested by Dask. So finally, what we'll end up doing is we'll end up calling map partitions on our initial Dask data frame and transform each of the partitions separately. Dask schedulers are interesting. The main options that I mentioned before were MPI for Pi, multi-threading, or multiprocessing and threading. Multiprocessing creates essentially a new Python interpreter for every worker you start up. Threading will share resources with different threads. This can end up making use of multiple cores still, but it requires that the underlying libraries be what's called thread safe. It means that they have to be able to share references and release the global interpreter lock and all of that. Pandas DataFrames is. The GDAL OGR library and R-tree are not. So the way that we're going to do this, since libspatial index and GDAL are not thread safe, is we're going to use the multi-threading approach. This introduces some additional hurdles involving memory handling because now if you create additional memory on every process, you're using multiplicatively more memory than you need to. This might not be a huge deal, right? If you have a lot more memory lying around than you have time to get a calculation done, you may be fine with that. There are ways to reduce that involving R-tree servers. I'll talk about at the end, but for now, we're kind of just going to ignore that and treat it like it's okay and we have infinite memory. All right. So when choosing this, unless we have some way of sharing, by default, probably the best idea is going to be multiprocessing. So for the way we implement this, we can first create a data frame from our tracked data. And then we can convert that into a Dask data frame. So that's what that second line is doing. The Dask data frame, we specified a number of partitions, and that's going to parallel the number of workers that we request, like the number of workers that are created, and the number of cores that we requested for our job. Because though there can be some advantage, you can take advantage of multiple workers on the same core. In general, having separate cores, we have full resources for each core, for each worker. You can scale up the number of workers basically just by increasing the number of partitions. So this gives us a very natural way to scale up a computation if we have more computational resources available. And then we will need a function that will execute on every one. So something that actually makes sense to implement a join on a partition by partition basis. So here, and this is where I'm saying we're being a little careless with memory, I'm importing GeoPandas and Pandas in each one. This is there's a lot of memory that's being added on, overhead that's being added on. And there are better ways of sharing other aspects of this, but this looks like a coherent block of code. This in and of itself, if run on a single data frame, this would be a join. Now we're just doing it on each partition. So conceptually, what you can see is the join structure here. So once we import our data frames, we're going to read in the Puma geodata frame and project it. We probably should have done this ahead of time and written it back out to save effort, but just showing everything. Then what we're going to do is we're going to create a data frame off of the tracked data frame. So what's being passed by Dask here is a Dask geodata frame. We may need to pass that to Pandas geodata frame and the version you're using, but then you can specify a geometry column and get a geodata frame out. So now that we have two geodata frames, we're free to use sjoin. The price we've paid is that we've built an R-tree for each geodata frame for each partition. This is overkill. Again, there's a better way to do this, but this would be a join whether it's parallel or not. And once we have the join data, we can create an output from that as a data frame and return that back, and Dask will handle that happily. So to actually call this, what we need to do is create an empty data frame with the output that we're expecting, because this is something that is going to make sure that Dask doesn't secretly transform data types for columns behind our back and doing something awful. And then we'll call map partitions, just like we talked about. And in our function above, we allowed for the path for the data source and the name of the geometry column, and then we are going to pass the specific to the field meta, this empty data frame, and that will make sure that our output turns out correct. All right. Oh, and one last note. In this, we used the Dask config set to specify a scheduler. I'm assuming we're working on a single node here, and I'm just using the single node style of doing this with a context manager. So that just means that scheduler is only being used locally for this operation. But yeah, that's how we're making sure that we're using, by passing processes to schedulers, how we're making sure that we're doing this with multiprocessing, and we're not going to do violate any threading requirements that we have in those underlying libraries to get incorrect answers. So how could we improve this? There are a lot of things that I've mentioned along the way here. We can reduce the memory overhead by loading these processes, the GeoPandas and Pandas ahead of time. This will create costs for sharing, but if you do it correctly, like the inter-process communication isn't as bad as duplicating the memory. We can reduce the memory overhead by sharing the target data frame to the worker processes. We can share as well as that. Like in addition to that, we can share an R tree for it instead of constructing it every time. So the whole thing can get shared out. Instead of building it for each one and taking extra time and extra memory resources to do that, we can do it once and share it to all of them. There's a fair bit of work that goes into that involving managers. And finally, we can subclass Dask DataFrame directly. They specifically reference to your data frames for this. Some of the things that I talked about in here, like meta and map partitions, are what you'd have to be extending and replacing in order to subclass Dask DataFrame. So I didn't want to get into a lot of class building examples, and other people are doing a better job of this, as I mentioned, with the work on geodatabases in Dask. There's a lot to look at there about how best to do that, but that's how you really want to make, what you really want to do to make sure that data sharing is not wasteful here between processes. So some final warnings. None of this actually makes sense if you don't have a very large data set you're trying to match. In Ravi Shankar's original work, here's dealing with 2 billion rows of point data that he was trying to match. Dask partitions are generally recommended to be about 1 gigabyte per worker. And the reason being, there's overhead with every task that gets created and every worker that gets created. And that overhead is not negligible. So unless you really have a good amount of work to do, you can end up doing something slower by doing it all with Dask in parallel. So definitely choose problems for this that are appropriate. R trees are good at what they do. That logarithmic search time is cool. You can get big problems solved quickly. So, a lot of things, if you just have enough memory resources for one calculation, you don't need to use Dask to do it. But it's a different story if you have a huge data set. When I said I'd come back to this, the R-tree server approach, there's a sketch of of this work done by Sean Gills, and basically the idea is that you're going to create a multiprocessing manager, and this will handle all the sharing out, and you'll register each function that you have to do in R-tree. This means understanding R-tree. You have to know how R-tree actually works. You can't just use spatial joins blindly. But it's relatively clear. If you're using intersect, you have to have an intersect function defined, that kind of thing. So once you register all the geometric operations you're going to need, and you can share those out through the manager, all the fussy details of locking and shared memory paradigms and stuff like this, all that's handled by multiprocessing for you, and the manager does, like class does that work. So it's an easier way of getting this this memory sharing improved. So that is the end of the talk. If anyone has questions, let's see if I missed anything here. Okay.
Yeah. Just letting you know, Ian, I think everybody's microphone does work. I encourage any questions right now. We're going to work on the slides there. The recording will be posted on the Westgrid training site in its entirety. I think Ian's going to pop his email in here.
Yeah, that's my email address. If you want to reach me and get a copy of it or anything else related to this.
Just give it a few more seconds for questions here from anybody. Feel free to open your mic. Don't have stage fright here.
Marcus, do you have a similar workflow for R?
Oh, for R? So, yeah, R does use the exact same underlying C libraries. So when you build the R, like the R geospatial libraries, they are also making use of GEOS and GDAL. So a lot of the same ideas are going to have like almost identical representations in R. And I can share some information on that later, but the parallelization I'm less certain of. I don't know. I've only seen on R I've only seen R used on a single node myself, so I can't attest to any equivalent parallelization. But you could do this with shared memory through persisted data subsets. So what you could do is you could chunk up your R data frame the same way, right? And then write those out to files and send those files to different workers you start up with different job requests. And then have each of those be separate jobs submitted, and they will run effectively in parallel. So that would be a strategy for getting the same kind of parallelization implemented in R, but I've never done it, so I can't say anything about how well it would work in terms of speed.
Yeah, conceptually it makes sense. I'm just wondering if there's anything like Dask for R. I'm not aware of, but I'm just wondering if there's any development in that front.
I don't know. Yeah, nothing that I'm aware of, but that my knowledge of R is less than my knowledge of Python. So, the question about the multiprocessing library in Python. That's really what actually we're using. Dask hides a lot of that. Dask is just calling multiprocessing. That's all it's doing once it builds these tasks. If you really wanted to slice up your data frame into blocks yourself and call the multiprocessing library, yeah, you're in business. There's no problem. The only thing is you have to make sure that the blocks you're sharing are actually suitable for interprocess communication. Right? And this is the same problem you run into with Dask is that when it shares certain kinds of objects, there's just a lot of overhead, and you have to make sure that you're doing it in an efficient way, and you're not disrupting some data structure that you're relying on under the hood, right? So the geodata frame has a common S index, right, for the whole thing. Because that's all, that is a reference to a particular expression of a with spatial index library, there's there are specific pointers involved. It's not thread safe, right? So when you share that out, I think you would have to either directly build that multiprocessing, the manager with multiprocessing, or you would have to rebuild it on each task the same way. But yeah, like in principle, you can get a lower level view of all of this using the multiprocessing library of Python.
Can you talk a bit about raster manipulation and multiprocessing?
So most raster manipulation are either element by element transformations or can essentially be expressed as linear algebraic transformations on a matrix. Anytime you're doing that, there is a whole body of parallelization work that's been done on linear algebraic transformations. You're transforming matrices, right? So all of this, in principle, falls under the scope of the BLAST standard and the various libraries for doing highly parallel linear algebra. These have been developed to an incredible extent. There's some very powerful libraries that back NumPy. So like MKL or OpenBLAST or Atlas can be used as a backing for NumPy. Those are then often used as the basis of raster transformations. Those can be highly parallelized. GDAL, and they're thread safe. GDAL is not thread safe, and I don't know if it actually, it's possible that the part of it that uses raster transformations, that is actually thread safe if it's calling those libraries. I don't know this underlying C code well enough to attest to that, but if you wrote your own raster transformations as matrix operations, yeah, you could just, that can even be done with multi-threading, and that parallelizes beautifully and scales up enormously.
Great, thanks.
Thanks. Take care. Bye.